Hello, am I audible to sir? Dr. Prashant Jain, sir?
Mayank. Good morning.
Okay. So, I welcome you all in the second session of today, that is third day of our FDP 3D printing and design. And today we have a speaker, Dr. Prashant K. Jain, sir, from Triple ITDM Jabalpur. It's my honor to be introduced, sir.
वो तो पूरा हेडफोन है ये वाला
Dr. Prashant Jain sir is an associate professor in the mechanical engineering discipline of the PDPM Institute, Indian Institute of Information Technology, Design and Manufacturing, Jabalpur, Madhya Pradesh, India. We call it is Triple ITDM Jabalpur. He obtained his PhD degree at the Indian Institute of Technology, IIT Delhi, in the area of additive manufacturing process. He has published and presented several research articles on part quality improvement in the SLS and FDM process in leading international journals and peer-reviewed international conferences. He is currently dealing with a sponsored research project as PI of a project titled Development of Additive Subtractive Integrated RP System for Improved Part Quality, supported by the Department of Science and Technology, DST, India. He is also actively involved as co-PI into ongoing research projects in the area of incremental sheet forming sponsored by BARC, Mumbai and Imprint India. Earlier, he has served as project scientist and research associate at IIT Delhi. His research interests include additive manufacturing, rapid prototyping and tooling, CNC machining, geometric modeling, CAD/CAM integration, computational geometry, human power energy devices, and nanotechnologies in manufacturing. So with this, I would like to invite Dr. Prashant K. Jain, sir, to start your session. Over to you, sir.
Thank you, Mayank. And very warm good morning to all of you. You can unmute yourself.
Sir, you can share your PPT now.
Yeah. Will the participants be able to unmute themselves to talk to me directly?
Yes, sir.
Good afternoon, sir.
Yeah, I just want that people should be more interactive. Otherwise, people will start their lunch.
Okay, sir.
There is nothing wrong in the lunch, but if it could be a one-to-one connect, I could have also joined. But this would be not good if I cannot join and everybody else would start their lunch. Now, can you see my screen?
Yes, sir. It's visible.
So, I hope by that time you have gone through some of the lectures on the 3D printing.
Yes, sir. We have completed 2 days with 6 session, and today itself we have a one session with Dr. U. Chandrasekhar, sir. So
Okay. Fine.
almost we have completed 3D printing of PLA, ABS, and metal also with their practical demonstration.
Right. Okay, so dear all participants, this session we have kept completely on the STL file, data preparations, error repairing. Means most of the time when you see the FDM printers, the videos of the printers or even machines are printers like that, and almost a very easy word like 3D printing, right? So as a engineer, we call it additive manufacturing, but now this is most commonly known as a additive. Instead of additive manufacturing, people know it's by 3D printing. So people sometimes thought that okay, anything just like our A4 size HP printer, we can type something on our computer system. Simply press the Control P and have a print on our hand. So, but this 3D printing is not that much simple. You require a lot of data preparations. Then you require a lot of slicing, etc., contouring, etc. Then only you will be able to print a good part. Like this part you can see on my hand. This mobile stand today morning my student has printed, right? So you can see the different surfaces, in fact different text if you can read it on this, and like this, these are the challenges you can see on the back side. There is a lot of waviness, additional parts are deposited like this, and on the front you can see the smooth surface like that. So while talking to you, I can keep my laptop in this mobile in this position. I can work, right? And then we made some design iterations like that. On the back side you can see we have created a hole to have the uh, this uh, hands-free or the charger to be connected, right? And the arrangement on this, like, so that we can keep phone in whatever the position orientation we like. But here what the point I want to make it that it's not that much simple. You can download some STL file and then you can give to your 3D printer, right? You can see here at the back side, if you can read it, some text is engraved on this, right? Can you see that? So I
Yes, yes,
understand
yes.
because I cannot see myself, my video. I am looking at my PPT slide. So, right, you can see there is some text. We have printed the CAD CAM lab because I have not reversed the camera to mirror position. So you might be seeing this in the reverse order, right? But these kind of manipulations are on the front. You can see here, if you can read it, my name is printed here, right? But at least you can see some text, if not exactly the mirror image, right? So here is this, what kind of data preparation required, what kind of STL file you require, whether your STL file is correct or not, all errors are removed, and it should be a complete volume pack, closed volume STL file should be there, right? So okay, so now let me come back to my presentation and look at this. Uh, what the principle you have already gone through, right? We have a CAD model, slicing of the model, squaring of the edges, then you have the staking and pasting of the layers, joining them. Did you notice the difference in the first figure and the fifth figure, the CAD model and the physical prototype? Anyone? Am I audible?
Yes, yes, you are audible, sir.
You noticed here the difference in two models, like here you see here you have the complete finished model, right?
Yes.
But here in the fifth model you got the stair steps, right? This you might have already gone through in some of the session, right? So here what happens with the materials related problems, we can have the minimum layer thickness, but this stair steps will remain there, right? We cannot remove it. So we require a lot of finishing approaches, post processing, etc., polishing, grinding, many things, right? So based on that we can get the full physical model, right? So that's the principle. Now come to the process chain. Can you notice on the top two cylinders? What is the difference in this cylinder and this cylinder? Anyone would like to answer?
So may I?
Yeah, please, please.
In first cylinder, that is completely uh, fine shaped, and in other there are some edges.
In other, what is that? Your voice is breaking.
Some edges are there.
Okay. Anyone else?
Maybe one is solid and other one is hollow. I'm not sure about it.
Okay. Okay. Anyone else would like to add to it? What is the
First,
difference in two cylinders?
first
Yeah.
cylinder is a fine one, and second one is a some dotted shapes is there.
Okay. Anyone else? Because in the entire session, key is in these two figures. What I am going to talk in this entire session on these two cylinders. What is the difference in these two cylinders and why this difference is coming?
Inside it is a model file, and the second image is the tessellation of the model. It is slicing. After slicing, it is converted to the mesh structure. It will be in model.
Okay, partially true, but that is not after slicing, it is before slicing. We will come back to details of it. Anyone else would like to comment on that?
So in that before slicing, the parameters like support generation, orientation, that parameters are considered for before introducing to the slicing. We are converting to a tessellation. That is, all triangles are linked together to form a one closed surface.
Okay, fine. Anyone else would like to comment on that? That will help me to how in depth I should talk about the STL file, their manipulations. Okay, no more. Okay, fine. Let me come back to the presentation. So look at this. In the first cylinder, there is a smooth, very fine cylinder, sculptured surface. Second one is the tessellation of it. And what is that tessellation is the piecewise approximation of a surface, right? And this piecewise approximation of the surface we have to do because our next step is to go for the slicing, right? In the previous slide, we have seen what is our objective or how we proceed with the layered manufacturing. We required a layered information. To get a layered information, we need to calculate the intersection, right? So to calculate the intersection, intersection of a very sculptured surface may be very high degree of the equation, 20, 25 something degree may be there. So it will be very difficult to calculate the intersection points and arrange them in a logical sequence. So what we do here, we tessellate it. Tessellation means piecewise approximation of a surface. So it can be anything. Like for example, I have just in the morning printed that soap case, right? So what is required? I need to convert this into the STL file before going for slicing. So STL file is a piecewise approximation, and how we do it. Suppose you have an apple in your hand and we ask you to peel off, but we will give you a knife, and suppose I ask you, you can use that knife only 6 times, and if you peel off your apple, what is going to happen? Your spherical apple will be converted in a, any idea what will going to happen your apple? Suppose you have this spherical apple and you peel it off. So 1, 2, 3, and the
We
4.
will have layer.
So 4 cut you put on the vertical sides, 1 on bottom, 1 on top. You see the lot of apple material would be wasted, right? And you will receive a cube, right? But this is required to have a planar section. Otherwise, you need to calculate the intersection with this apple surface. But now you need to calculate the intersection with a completely vertical surface, right? And this in this case, if you cut in this way, it would be a square or rectangle, right? To maximize or minimize the volumetric loss in this case, we keep the triangles. You look at on this cylinder, all are the triangles, right? See, all are converted into the triangles. So even though this is a rectangular face, can be represented by a rectangle, but still we use to maintain the standards and uniformity among all the models. So we have the triangles, right? So this is the tessellation we do, and this tessellation will help us in the slicing, because next step to have the slicing. So if you see, I slice in this way. Here, this slicing calculation of intersection points would be very tough, but here you see what has happened. Now this line or this plane in a 3D space, it would be a plane. It is intersecting with another plane. That plane is also a triangular plane, and the triangle planes is also have a 3 straight line. So finally, your problem is reduces to a intersection of a plane with a straight line, right? That is the tessellation, and what we call in terms of our data format the STL file, right? So anytime whenever you go for a 3D print of any object for any machine, you try to get its STL file. Now what is in that STL file? Your surface was approximated by the triangles, right? By the planar sections. So we go geometric model, tessellation, slicing, then we generate the laser scanning path for one each layer. This is a single layer, right? This is slicing, and from based on this slicing, we generate the laser scanning path, right? For SLS process or metal process or any other process, right? At this stage, we are not going into any details of the process. Then we have the part fabrication, then post-processing, right? So look at this, how we implement this. See, one geometric model created in ProE. Now, when we import this in the MATLAB, you can see here. Here there is a planar section. So what happened to this planar section? Now this is converted into the STL file. So you have this one triangle, another triangle. On the top surface, you can see this top surface, 2 triangles, one, another one, right? But you see for the circular face, we have hundreds of triangles, small size triangles. Why we taken so many triangles? To approximate the surface more accurately, right? If you take only 2, what will happen? Your lot of material would be wasted and it will be sliced like this, right? So tessellation in this way, not possible. Now look at this, when we try to calculate the intersection in the MATLAB, see in this STL file is imported in MATLAB. I will show you the files little later, right? And you can see here the green color plane is there. So that is the intersection plane. And you can see, can you notice what are these blue dots here? Anyone? What are these blue dots here? Anyone would like to mention?
Sir, is it for support material which is to be drilled out?
No. Anyone else? What are these blue dots? Blue colored dots. You can see on this model, and you just I will give you the hint. They are appearing at the plane of the intersection plane. So here you can see at this stage we have taken a plane of intersection. to intersect this model to get the contour information. You see here, let me zoom it. Now can you see?
Lattice point.
This is intersection point, right? That is the intersection point. The green color plane is there, and this plane is intersecting with this solid model of STL file. So what STL contains? STL have the lines, right? So you look at this here. This line is coming from this end, and this plane is coming from this end, right? So you got an intersection point over here, right? And when we connect all these blue dots, what is going to happen? We will receive a, if as and when we receive this blue dot and I plot, I will get this kind of information. Got it? But this information has no use for us because we want to print this part, and for printing of this part, we want first layer, second layer, third layer information, and between that, the nozzle path is required. So we need to connect all these dots in a logical sequence. Look at this. When we apply some logic to connect them in a sequence to get the contour information, what is going to happen? We receive this blue color contour, right? And the red color contour. Can anybody tell me what is this red color dotted line and blue color line? Anyone? These lines? Can you relate this figure with this figure? At this stage, if I cut this geometric model at this height, if I cut this model at this stage, we will receive this information. So you see this blue color is external contour, this one on this model. And this red color dotted line of this internal contour from here. Right? Did you notice this? Right? Now look at this figure. From here we can have right? We can draw this kind of external lines, right? And from this you can see here what is going to happen for this nozzle will be here. You have to switch on the nozzle. Here you have to again switch on this. Here you have to again switch on this nozzle, right? This is going to happen, right? So what is happening if I draw a line over here, we can identify based on this contour intersection points, right? At this contour, the nozzle will be switch on, and here the nozzle will be switch off. Okay? So what will happen? Material will be deposited here. The nozzle will continue to move here. Then here again it will switch on, again it will switch off. Right? This point is clear? So that is the requirement for the STL file. We require the STL file, right? Now look at this, how we make the model. Have you gone through this software screen before in any other session? Then I will skip or else I will show you.
No, sir. It's first time that we are seeing that magic software in this FDP, sir.
Okay, let me run the Magics directly. Look at this. That's the magic software you have. You can rotate like this. So you see here, we have manipulated this STL file and written the IIT Delhi file, right? And I will show you the original file as well, right? So this is the geometric model you might have can create in UG, CATIA, ProE, Unigraphics, anything, right? And then you have to take it to the magics for error repairing, etc. I will talk you in detail about what kind of errors we have, right? So look at this. These are the so many triangles you have, right? If I zoom it, you can see here how these similar triangle, then here the smaller triangles at the cut portions, right? Right? And then you can see over here, even in this spring area, right? You can see how small triangles are there, right? Now, if I take a cut, how 3D printing takes place in this case, whenever you take any model, any sort of model, yeah, let me place in this position. Let me take it to back and go for a section. Right? Can you see over here? This is the section model. So if you start from bottom, this is the first contour, second contour, third contour, like this, n number of contours. So here it would be a complete circle, right? That is the objective why we are talking about the STL file, right? You see at this stage only this is the material to be deposited. If it is a SLS process, right? And if it is a FDM process, the nozzle will deposit only this much material. You see here, and at this stage you have only one sphere, right? Now second sphere comes into picture, and clear gap between two spheres provided by the unsintered powder in case of SLS process, right? Look at this, third sphere comes into picture, and subsequently it will getting on, right? And look at this here, this contour information is required. You can see here, this is the contour information we want on each layer. And if you look at here, this in the triangular form, you see these triangles are cut and the intersection points are calculated at this level, right? You see here, this is a intersection point, this is another intersection point, and these are connected in a closed loop, right? So many contours on the same layer even you can have, right? Okay. If you have any query at this moment, you can ask. Then I will go back to.
Sir, I have one doubt.
Yeah, please.
So if you are using FDM printer for printing this spherical ball, the support will be provided inside. How to remove that support?
If your support is water soluble, that you can use. And if not water soluble, then you will not be able to print. Look at this. It has broken down because this ABS material does not provide that flexibility to print the strength, right? So it has broken down, but this is printed on FDM only. But this is a Stratsys MC400 machine, right?
Okay,
Okay.
sir.
You see the three balls are there inside this, but that spring and the stand was broken down. So there is two nozzles in FDM process. You already gone through. We will not go into back, right? But point was that another nozzle we use the water soluble material, so that will dissolve in the water, right? You see, that
Okay,
is
sir.
the only way we can print this kind of fully functional assembly. Right? You see, this is again printed on FDM, and you see there is inside proper tolerances are given. So if we use the single material, they will join. So we use two material. For support, we have another material that is water soluble. Okay,
Okay, sir.
fine. Okay, let us come back to. Okay, I hope you can see my presentation screen.
Yes,
Right?
yes, sir.
That's the part I have shown you, that the STL model. Look at this. Actually, this STL part was having this kind of text, and I have manipulated it. I have changed even the STL file without going to the original software which have model it, right? So you see it here. You see the IITD. You can see here, right? Clearly mentioned here IITD, and here you see it is US, right? Okay, so now this is one part of the introductory I have taken. I hope you understood the need and importance of the STL file and why we are choosing this topic to be the part of this FDP, the STL file manipulation, right?
Sir, excuse me, sir.
Yeah, pardon. Anybody wants to speak something? You are
Yes,
open.
sir.
Please share
Sir,
your view.
I have a question, sir.
Yeah, please.
Sir, your drawing, whatever you have shown now, it is been meshed, isn't it, sir? That
Pardon.
you have measured the component that you have shown it now, sir.
If you talk in terms of FEM, you
Yeah.
can call it mesh, right?
Okay. Yeah.
But what has happened when you talk about the FEM mesh, that can be a many type of mesh. It can be a brick element, it can be a tetrahedral element, right? And it
Yeah.
can be anything, right? But
Okay.
and it can be a solid as well. But when we
Yeah.
talk about the additive manufacturing process, 3D printing, we are only talking about the surface model, not solid model. So that mesh, you can also say it is a mesh because it's a similar process, right? Right. So
Sir,
it's a Denali triangulation, and we divide the entire surface in pieces of
what is
planar
the
section.
purpose of this one? What is the purpose of that dividing?
That is the purpose. That is what we talk. Okay. Okay. After a few more minutes, I will come with another slide. So that will be more clear why we are doing this tessellation, right?
Okay, sir. Thank you, sir.
Fine. So now let it come back to the more technical side of the STL file. Right? This is what we discussed. You see the small rabbit and a lot of triangles are there on this to model it, right? You could have a smooth surface, but we have chosen only the triangles, right? So that we can slice it. That is the purpose, right? So look at this. If it is a cuboid, this will be represented in terms of triangles like that only. So what this STL file have, the correct, we have this STL file to represent the triangles, but it has to follow certain rules. What are those rules? Look at this. The number of faces must be even. Number of edges must be a multiple of 3. You can understand. You can say very small rules. Matlab, if you have a cuboid, so how many faces you have in a cube? Anyone would like to answer?
6 faces will be there.
And when we convert this into a STL file, because we have to take everything in triangle. So how many faces we have?
6, sir.
12. In that case, because you need to convert this into a triangle. So all 6 faces are rectangular in nature, right? So when you convert this in the triangle, you have now 12 faces. You can observe here, you have this one face, another face. Earlier it was a single face, right? Now you have these 2 faces. So you will have 2 faces on top, 2 faces on bottom, and then all 4 sides. So you will have 12 faces. Now you look at this, every face have 3 lines, right? This face have 3 line, this face also have 3 line, right? So definitely if you have 12 faces, then the number of edges must be a multiple of 3 if file is correct. You got the point? Why we are talking about these rules, right? 2 times the number of edges must be equal, 3 times the number of faces. Simple equation of Euler's formula for checking the wireframe models, right? And then how we write the STL file, right? So this has already become a standard. Whatever the free or open source software you use, whatever the model you have to use, whatever the kind of machine you have, whatever the kind of technology like FDM or SLS, anything, what has happened? We have the STL file as a standard, right? So we use this to generate a 2D contour, right? So look at this again, few more rules. The file will contain 3 vertices, right? Say this one vertices, this one vertices, this one vertices. 3 vertices for each triangular facet and 1 normal pointing towards the outward, right? That is the scene in the previous slide I have shown you, right? So you have the 3 vertices like x1, y1, z1 and 1 normal, right? So total 12 floating points are there to represent a triangle. Okay. Now here we have to identify which side of the face is interior, which side of the face is exterior. So the normal will tell us, right? And further rule, if we talk, the each triangle must share 2 vertices with each of its adjacent. You see here, when I say each triangle will share its one of the edge with another triangle, what practically it implies? That means there is no gap. These two faces are closely joined with each other, right? If this edge is not shared by these two, that means what has happened? There is a gap. We will come little later on that gap, right? So we have here, I think some slides I might have. Let me check once. I think 1 or 2 slides are kept hide. No, it's okay. Fine. So we have 2 kind of formats like ASCII and binary, right? What has happened? ASCII have the more descriptive and human readable, very large size of the data. You can see here. Only for 12 triangles, we have the size 684 byte, right? In case of binary. And in case of ASCII file format, you see here 3417, right? So ASCII file have more large size, but it is human readable. That is the important. Binary file is more compact. We cannot read by our own self. We cannot understand by our own self. Otherwise, see for some examples, like for example, this is the cuboid, how the STL file is written. Have you ever tried to open any such STL file, .prt file, .slrd file on the WordPad or your notepad? Anyone? Have you ever tried to open? Have you ever noticed, even in your MS Word file, when you go for save as, how many different kind of file formats are available to you? Anyone would like to comment on that?
Sir, we have not observed it, sir.
Pardon?
We have not observed it so keenly, sir.
Yeah. Here we have to be to observe. You notice a lot of things. You see, this is the STL file. If we open in the WordPad, see, I have here the 2 files, and that is the structure difference you see. In the first file, if you notice here, let me open it. This is the file generated from. Okay, this I have opened in that print 3D, right? This is a cube, right? So this is the cube STL file you can create in ProE or anything else, right? But when you open this file in the WordPad, you will find this. This kind of text is there, right? And if I create the same cube file, this is from SolidWorks and AutoCAD, and this is from the Magic software. This is the difference in the structure. You see how the information is written in this form. Let me run a MATLAB program, then I will come back to it, so you can have a better understanding. See here, I have written a small program to read that STL file. Just like your C program, a small program is here, but this program will open the STL file in MATLAB editor, and then read one line each time, then store all the coordinates in a form of a matrix, right? So if I open a cube, this is just we made it like that, so any professional program like this is not a any open source utility, it is self-developed program. So let me open this file. Okay, look at this, here is the 12 triangles, right? And for each triangle xyz of one triangle, and this is the normal. So you can see it's keep on changing. First line is the normal and other three are the coordinate, right? So this is for 2 times we have run. This is for first phase, second phase, third phase, fourth phase, like that, right? So this is up to 12 phases. This is the 5, right? And you see in the MATLAB. How many of you are aware about the MATLAB programming? Anyone?
Oh yeah, little bit.
Sir, we learned it, but we didn't practice. We don't have practice on that one.
Okay, what here I want to emphasize, if suppose we want to pursue our career, our research in additive manufacturing, we should know how to intervene with or how to manipulate the STL file. We cannot every time depend on the commercial software, because when commercial software will generate any STL file, it may have a lot of errors. And for any kind of research activity, you may require to generate your own tool path, right? So you cannot generate, because you until unless you do your own programming by your own self. Otherwise, you can print this kind of part. No, but suppose you want to vary the vector length, you want to vary the width of this, or some other process parameter you want to vary, that may not be possible in that commercial software. So look at this. This is one. Let me open another file with this program.
So I have few,
Yeah, you can ask
which
question.
add-on will be used for plugin in MATLAB?
MATLAB for what plugin?
We are using like for simulation, like linking mechanism. Simulink will be used for add-on in
No,
MATLAB.
MATLAB have more than 50 toolboxes. But here, what I shown you this program, to open the STL file, there is no plugin available, kind of thing, right? This is to the user development program.
Okay, sir.
Okay, like now you look at this. If I use another file, it will not accept. Look at this. If I run this STL reader magics file, and if I open the same file which I have already opened earlier, right? This file. This doesn't work. See, both the files are written specific to the program. The reason is this: the file exported from SolidWorks and AutoCAD have a different structure, and the file exported from the STL reader magics have a different syntax is written. So if I want to run this program, or if I want to read a magics file, I need to modify my program. Look at this. I open this file. Now it's working fine. Got it? Right? And you see, if I go back and let me open you that file. Right? I have opened this file. So here we have an advantage. You can open and you can see in the WordPad, right? Look at this. You try to do this. Look at this. This file is written in this way, right? And the earlier file I have shown you that one, right? Look at this. That is the difference in these two files. I have shown you in the PPT slide, but look at this, how this syntax is. Here the scientific unit is there. Here the simple decimal unit are there. Everything is left aligned, no tab spacing, and here the tab spacing. So when I did this programming at the start of my PhD program, I was worried. I have written a very good program to read an STL file, open it, do the cross sectioning, do the layering, generate the nozzle path. But one day my another fellow researcher came to me and said that, okay, Prashant, please do the slicing of my part, and my program was not working. Then we realized what is the difference. Then we got to understand, because I was using the Magic software, so my file is for in this format. And he was working with SolidWorks, so he brought me this file, and my program was not working. Then we did lot of understanding, developed that how I need to modify program, where to modify, right? And here you see this STL file, even we can write without even going for Magix or Pro-E or CATIA. And I will make you understand. Look at this. In this case, I have taken, sorry, this way, right? So look at this. I have used it here. I have taken the center at the origin, right? And now you can relate this file. See, because the 10 mm cube is there and the center at the origin. So all XYZ dimensions will go up to the +5 and -5 of the corner points, right? You can read this word file and you can understand what kind of cube is there, where it is placed even, right? And if I open another file, you look at this, sorry. I have taken this cube at the 0, corner point at the 0 position. Look at this, what has happened? The every unit has become 10. So starting from 0 to 10, right? And if I open this file in the MATLAB, let me run. Corner at 0, right? Right? You can see here is 0, 0 is corner, right? And in the previous figure, it was 0, 0 at the, sorry. See the difference? So you can relate. It's center at the origin and it's corner at the origin. Got it? So this is how we need to develop our own understanding about the STL files, right? That is the objective here to discuss. Okay, let me move something more. If you have any query at this stage, please ask. Let me close all these files. Right, so that is the thing. Two things I have shown you, two files. In this, you can see only this difference. The cube Magix is in the corner is at 0, and here the center at the 0.
Excuse me, sir.
Yeah.
Sir, the STL programming that you are saying it, is it to repair the non-joining surfaces, or
Yes.
we can change the dimension of the component itself?
Yes, of course. You, if you want, you can go to your WordPad file and you can change the dimension. Instead of 5, you can make it 10, 25, and make it consistent. So even without going to Magix or Pro-E or CATIA, any other software, you would be able to change and manipulate even your STL file on your WordPad itself.
Can I save that? Can I save that to modify the diagram as a CAD drawing again?
Yes. Yes. Nothing is wrong in there. You just go to the Word file and you can just simply save it. as it is with .stl extension. Don't change the extension. I will show you. Yeah,
Okay.
please.
Sir, can that HTL can be changed to the CAD drawing?
It is until unless you keep it in the .stl file format, it will remain a STL file.
Okay,
It
okay.
cannot be go back to the .prt file because you have already tessellated. So a lot of volumetric data is already lost, right?
Oh,
That cannot be kept back now because it's a designer intent. If I delete a facet, we can join that facet. But suppose at that location, suppose 2 or 3 facets, we not be able to understand knowing what designer might have intended. But you can make manipulation in the WordPad itself and you can save those changes.
okay. Thank you, sir.
Okay. Anybody else have anything else? Okay, if no, then we can move ahead. So let's talk about the advantage. Simple to understand. You can see like that how simple it is. We can open in WordPad and we can see what is there. Then
Hello.
Yeah, just take a pause of 5 minutes. Let me complete 2 slides. I will get back to you for all the questions, right? Then any kind of geometry can be tessellated in STL, right? Then it's already a de facto standard. Everybody knows about the STL. A lot of books are available. All manufacturers, supplier of the 3D printing machines use the same standard, right? But now there are some disadvantages as well. What are those? First thing, non-usefulness of the polyhedra. What is happening? We are using only the triangles, right? But you might have seen if I have a cube face, which is already planar, I don't need a triangle. Even my rectangle would be sufficient. So we are using the lowest of the polyhedra of 3 sides, right? So we are unnecessarily increasing the size of our STL file, and many a times the file size may be much larger than the original CAD data, right? And because of you do the tessellation, so already volumetric loss would be there. Then we have lot of redundant information. You see here, these are the 4 triangles, right? So this point can be common. But what happens in the case of STL file, every triangle will be written as a separately. So what will happen? This point will come 4 times. Similarly, you see here this corner point. How many times this common vertices will come into the STL file? Can you make a count of this? This particular vertices, how many times it come in the STL file?
Four times, sir.
1, 2, 3, 4. 4 faces तो आपको सामने दिख रहे हैं. There will be 2 more faces on the bottom side as well, right? So
6 times.
might be 6 times, might be 5 times.
Okay.
Right? And now if you see, if this is the vertices, this is coming how many times? 1, 2, 3, 4 times it is coming. Right? So very much redundant data. Similarly, you see this common edge. This edge will come in this triangle as well and another triangle as well. Right? So a lot of improvement can be done with the STL file, like better accuracy in representing cut surfaces, surface texture and requirement, buildability verification, like you can check whether any leak is there or not, then inclusion of metadata, etc., which is not possible at this moment. So people are working with the STL file as well, right? Another situation will come like this number of triangles. You see, this is the same geometry. Both the geometry are same, but here we have approximated with larger number of triangles. So only 8 triangles here, and here the larger number is 945. See the huge difference in the file size. Look at this. And in this case, only 8 triangles, 2285 is the file size, bytes. And here you see 2,67,000 bytes. Same file, depending on the number of triangles. Right? So here, this is more close to the original geometry. This is a very rough approximation, right? So these things we control in the STL file, like parameters, the chordal errors, right? Angle control. So two things would be there, right? Here to control. And that will vary the process parameters, right? So like chordal error means, say for example, this is the curve. And you are approximating as a planar section, so you can cut like this. You will cut like this. You will cut like this. So here you see this is the gap created, right? This gap, this distance in between these two, known as the chordal deviation, right? Similarly, the angle control. If this is the point, now you start cutting like this. So that angle, we measure that angle. So depending on these two values, right, the number of triangles will keep on increasing and decreasing, right? Look at this. What is happening here? If I have this situation, triangle 668, the file size is this. We increase the triangle up to 1086, so this file size is. Look at this, 1380 triangles, the file size is this. All three are the ASCII file formats. Number of triangles are keep on changing, right? Fine. So that is the why we should understand about the file size. Why most of the time you look for the 4 GB RAM, 8 GB RAM, i3 processor, not working your PC or laptop. Your laptop is overheating during file tessellation or slicing, right? So that kind of situation may come, right? So we control these tolerances values and accordingly we change the number of triangles, right? So two tolerances, deviation and the angle tolerance and chordal error deviation. Right. Now, what is the reason for these bad STLs? Right. If you remember what we discussed, we talked about the adjacent triangle must have two vertices in common. The orientation of the triangle, right? What side of the triangle is in and what side is out, right? And the normal must agree. So if any of these criteria are not matching, right, the problem exists in the STL file, right? So like this, several problems in the exist, right? And commercial tessellation algorithm we use while exporting the STL files are sometimes result in a approximate polygon, right? Which exhibit like gaps, means crack, holes, puncture, the missing facets, then degenerate faces become all facets become collinear. I mean all vertices become collinear, right? So your triangular facet will become a straight line. Then overlapping facets, then non-manifold topological conditions, right? So these are the major problems. In this today's session only we talk about the first problem, gap, right? So you see, look at this kind of situation. Very large deviation in the curvature is coming, right? So that will not be able to your software, because you might have taken the tolerances which is larger than this. So what your software will do? Software will not create a face over here. So there will be a hole, and your machine will not be able to print that part. Look at in this case in much better way. See, this is the top surface, this is the vertical surface, you can see. So the tessellation you do, but here what is happening? Because of your tolerance set, you might have set the tolerance limit say 2 millimeter, and this gap is within the 2 millimeter. So here this is the gap created. Now because of this gap, what will happen? Your STL file will not be a closed pack volume, right? Because of this, your STL file is not closed pack volume. You will not be able to slice it. Similarly, you see here, if the situation like degenerate faces, this situation can come. Like this is another surface, this is another surface. So at this edge point, this complete triangle has become a straight line. Now you may ask, what is the problem with the straight line? Right? Can you tell me, suppose I have this pen in my hand. What is the normal of this pen? Okay, before pen, let me have a, okay, this box. Right? This is the plane surface. So anyone can say where is its normal? This is the normal to this plane, right? Can I say this is the normal to this plane? Anyone would like to answer?
Sir, line parallel to the earth surface.
Right?
Line
Now,
parallel to.
yeah, pardon, please.
No, sir. Please continue.
Okay. In this situation, I can say this is the plane and this normal, right? This is the normal to the plane. Now, what happens? My plane itself become a straight line. What is its normal? Its normal is like this also is the normal, this also is the normal, this also is the normal, right? Now all 360-degree angle, it will be a normal. Got it? So my software, my 3D printing machine will get confused, which is the normal. And why I am asking for the normal? If this is the box to be printed, this normal will tell this surface is the outside surface. And within this is the solidification material required. So material to be deposited here, not here. Right? So this normal will give me a closed contour because this is external, this is external, this is external, this is external. So on these four sides, it will be external. I can get this contour. And material can be deposited in this contour. But suppose I don't know where is the normal. We will not be able to decide which side to be printed and which side not to be printed. Got it? So that's the issue. We need to calculate the normal. Okay. Now, yeah, if you have any more questions, please ask at this moment.
Sir, what is the relation between the nozzle movement and the slices that you are making it? Where does the nozzle, from which point to which point the nozzle will move and deposit the material?
That is up to the software. Quite possible even in this case. Suppose okay. Suppose, say for example, this is the part you are going to make. Okay, keep it on this. Say for example, so your nozzle will be starting from this point, moving in this point like this.
Okay.
Right?
Okay.
So that you can fill this part. Now, quite possible you have this kind of part, say for example this, and you have inside there is a hole. Now your nozzle will be starting from this point, coming from this point, moving like this. Now what will happen here? You can adopt this strategy, lift the nozzle up, move into this, lift the nozzle up, move into this, and continue, right? Quite possible you don't go into this side and keep on connecting. A lot of research papers are available in the nozzle path, right? And then you left out the remaining area, right? That is a completely different topic right now, I would say here.
Sir, how does the slicing in the manufacturing? What is the actual role of this slicing? Where does it help us?
Because when you see in the 3D printing, you've gone through many sessions, you require a contour information. So what do you mean by contour information? Contour information is the layered information.
Okay.
So until unless you have a layered information, how will you deposit the material?
Okay.
Got it? Because
Yes,
see, let me give you another example. Can you see I have a tea coaster in my hand?
yes, sir.
I hope you can see the different layers. So say for example, this is a complete part to be built through 3D printing.
Okay.
So what 3D printing will do? 3D printing will make the first layer. Once this done the deposition of material on this first layer, then it will take the second layer, third layer,
Yes, sir.
fourth layer, fifth layer, and sixth layer, right?
Yes, sir.
Now, actually, what is required? You have to make this solid part. To make this solid parts, what you need to do? You need to cut this solid part into the 6 layers.
6 layers.
And then you start depositing the first layer, the second, third, fourth, fifth, like this. But actually, this is a single part. When you make it in CATIA or PROE, you made this part.
Okay.
Now, in this case, I have taken very simple part. So what happens? All the 6 layers have the same geometry. Right? But suppose you take this mouse and cut it, you will not have, because you will not have all the layers have the same contour, right?
Yes, sir.
So you get this contour information and then deposit the material. That's why this geometric model you need to do first STL file, tessellation. Once you do the tessellation, then you only get the contour information. Let me show you how we do this. Others, please wait another 10 minutes. I will be closing. Let me conclude this in a complete manner. Right? So there are so many errors in the STL file, right? Like flip triangle, bad edges, near bad edges. This is flip triangle, bad edges means not are connected. You see the hole. On the top surface, there is no face. There should be a triangular face, right? Here also the tessellation to be done, but the software failed to do it. So this is a hole. Lot of holes. Now see, before repairing, we will not go in today's session for repairing, but look at this. What happens if I do not repair, if I do not validate my tessellated model? See here, we have this model. This kind of slicing is required and this nozzle path is required, right? So we cannot directly slice it. So what we do here, we take that the same model, we tessellated it. Tessellation meaning is clear now, we triangulated it. You can also say we meshed it. Then now we take a plane, right? And do the slicing. So what happened here, there is a surface. So you will receive this point, and this point. But here what has happened, you see the gap is there. The hole is there. So if you cross section it, what will happen? You will receive the contour from this point to this point. And here you will not receive any line. what will happen when your nozzle will start printing? Nozzle does not have anything here to close it or come back. So what will happen? Your nozzle will start to move to infinite distance, right? And your system will hang here. Your software, your nozzle path cannot be completed because there is a gap in the STL file, right? Fine, that's the issue. That is the purpose. Somebody has earlier asked also why we are doing the tessellation. That is the reason we are supposed to do the tessellation, right? Because otherwise, no predefined stopping boundary on a particular slice. So the building process would continue right to the physical limit of the RP machine. Right? And a lot of solutions are there to repair the STL file. This is what I have already shown you, right? And when we repair the STL file and we create a new loop into that. So instead of going this complete algorithm, I will just try to show you this, how we implement this STL repair using MATLAB program. Can you see here? Two facets are missing here, right? When we try to fill it, the blue color filled it. But now remember, your solid STL file is closed now, volume pad. But this was not the original. Orientation may be different. So we can check the alternative orientation, and now you see your cube is completely closed. And somebody was asking, can we save that? We can also save that. Let me run that program. Let me show you the run point, STL crack repair, right? So we can run and see. I will take a STL file, which is okay, only one hole, right? Look at this. Can you see this STL file? Can you see some lines over here? Let me make it full scale. Can you see in this file? No hole at this stage, no hole, no hole, no hole, but let me keep on. Can you see? We see the inside lines over in this direction here. There is a one face missing. Right? Now look at this. If I go back, let me fill the hole. See, now this hole is filled. Right? And now this is the revise. So we can save this file. One, to correct the orientation, two, to generate the file. So it is asking me for the name. Let me put pkj. And in the new file format, you will see that pkj, this STL file is created. Look at this, the solid corrected file by pkjain. pkj file name we have given. Look at this. Got it? So in this way, we will develop the algorithm and we will repair the algorithm, right? Right, at this stage, if you have any query, please ask me.
So
And
first, like,
you can connect me on LinkedIn at PKGen 2006. Connect me at Facebook PKGen 2006.
Sir, this is Mansi Jain. Sir, I want to ask a question, sir.
Yeah, Mansi, please.
Sir, the softwares like ANSYS, Additive, Flow 3D, and Comosol provides simulation aspects of the additive manufacturing. So there we cannot improve the STL files.
No, you can improve a lot. But point is this: suppose I have to give a shrinkage compensation to the nozzle path, and that nozzle path is varying depending on the length of the vector. So no commercial software will address this issue until unless I know I sliced my STL file, I calculate the nozzle total distance travel, and accordingly I can modify the point. Otherwise,
that
what
is
will happen if you take any software and ask for the shrinkage compensation, say 1% shrinkage compensation. So it will be uniform on the solid model along x-axis, y-axis, z-axis, all three. Or even if you vary in three different directions, but the entire layer will be extended. But suppose I want to give a small variation in one vector length, that is only possible if I know how to manipulate the STL file, how to repair the error.
Okay, sir. Okay, sir. I got the point. Thank you.
Excuse me, sir.
Please.
Sir, while discussing this slicing, you said that a cube you have taken, each side it is dividing as two triangles.
Yes.
Okay. So what is the need of dividing it into triangles?
That is the what point I told you earlier. Because we could have run with a single rectangle as well, but we used to take the triangle because the smallest plane is the triangle, right? If I want to approximate any surface, the best possibility lies with the triangle. If I take a rectangle, there is a quite possible to have a volumetric loss.
Voids will be there.
For example, this is the plane object, right?
Yes, sir. Yes, sir.
But this plane object is like that.
Oh.
So if I represent it as a rectangle, quite possible it may lose some.
Yes, sir.
Actually. Say for example, right? And if I can hold it like this, if you can visualize it on this camera, I am not sure, right?
Yes, sir.
If this is the object, and if I try to represent it as a rectangle, what best I can do, I will connect all four corners.
Yeah.
So some volume would be lost.
Yes, sir.
But if I use triangle, I will be more close to the geometry in my hand.
Yes, sir.
Got it? So that's
Yes,
why we take the simplest and smallest polygon, that is the triangle. We can also use the higher order polygons, no issues.
Sir, is there any textbook or which is giving more details about this STL?
Whatever I discussed today, you can go with Chi-Fi and Chua as rapid prototyping theory and principle. Yeah, right now not in my office. Otherwise I would have shown to you. Let me. We periodically conduct a lot of programs. Gibson, Roger, yeah, this one. This third one. Rapid prototyping principles and applications. Chua et al. This book you can refer for the entire STL file.
Thank you, sir.
Okay, so shall we close this meeting? Yeah, you are also close.
Sir, thank you for an excellent practical session, sir.
Thank you,
Many.
everyone. And we will be connected, be in touch. We conduct lot of programs in specific areas of like biomedical applications of additive manufacturing, the MATLAB programming for additive manufacturing, and we run in the periodical program. I think in how I have come across with IPS Academy. Uh, so like that.
Sir,
Thank you, sir.
one participant is asking in chat box that if there is a complex STL file, MATLAB will provide editing.
No, no, no. MATLAB is not providing any editing. We have to create our own programs. So that is how we understand, right? This is not possible. Okay, like that MATLAB will do everything for you. Within the MATLAB also we need to develop our own program.
Okay, sir.
Slicing mathematical equations, which book we can? Yes, slicing actually the time is limited. Otherwise, I would have solved here itself how we develop the equations. Let me read out. Yeah, Python coding is also okay. If there is complex STL file, MATLAB will provide edit. Yeah, that depends on how robust you make your program. I have my program. I can open any STL file, I can edit. Slicing mathematical equations, which book we are? Yes, no sir, which add-on is okay. What? Python coding is also okay. Just simple it is for STL file, the slicing also, but today we cannot cover everything in this session only. But a lot of algorithms are there. Even we can develop our own mathematical equations to run this. Can you see my screen, PowerPoint screen?
Yes, yes.
So look at this. This is another aspect of the programming we have discussed up to so far, right? Up to error repair, we will go for the slicing. So when we do for the slicing, we need to check, find it out how the internal slicing would be done, external contour, right? And then we write the information in CLI file. This has to be used by the machine. This is another format for this CLI file, right? And this is how we take the STL. So everything would be converted into the triangle, right? Then we have the contour. This is the reason why we take in the triangle. Now look at this. We have to calculate only 2 intersection points. And a lot of equations we can develop. But slowly we can move on developing the program in MATLAB, right? So this is how we do the slicing, then contouring. This is all we have implemented in MATLAB, right? So any other time we will discuss. I would welcome the interested user to write to me on the mail and on the Facebook as well, because everything and sometimes it may become boring also if I go into the much detailing of the computation part like in FDP. Okay, so
Okay, thank you very much, sir.
okay, thank you everyone.
Hello, am I audible?
Yeah.
Thank you very much, sir, for your nice and wonderful session. You just uncovered the STL aspects of this 3D printing. Generally, we just cover the STL and goes to the 3D printing. We do not so much care about the editing and all this. And you have covered this STL file manipulation and data preparation for the 3D printing with usage of Mimics and MATLAB software. Hopefully the participant will get the idea for the manipulation, and we will learn in future with some exercise and tutorials with you, sir.
Yeah, Mayank, just one more minute. Somebody was asking why we are doing this, to highlight the importance. Just let me show you another video.
Yeah, sure, sir.
I hope people are here, not went for the lunch.
Yeah. It's
Can you
still
see
live,
my
sir.
screen? And just where is that video? Can you see video screen?
Yes, sir.
Can you also listen some sound of the machining
No, sir.
now? Look at this. Actually, this is a one of our DST sponsored project, hybrid additive machining. I'm showing that video, right? So we have deposited the material on the CNC machine itself, you can see, and we are machining on the same setup, right? So you can see this video. And if I do not manipulate the STL file and generate the tool path by my own, I can't do this. So we have manipulated the STL file, calculated all the coordinates, converted those coordinates into the G&M code program to be run on the CNC machine. You see, that is the deposition. And this is the reason, if I do not develop the program by my own, we will not be able to work with the only depending on the commercial software. So look at this, the material deposition takes place, and you can clearly see the STL formation on this. Right? So that is the reason, right, why we should know much about the STL file, toolpath generation, CNC machining, G&M code. All these things are related, right? So I would say all interested participants, you be connected with Facebook. Whenever the new program or something comes, we will keep on sharing on the Facebook.
Sir,
Okay, Mike?
Okay, sir. Thank you, sir.
Sir,
Yeah.
can we have your email ID, sir?
Yeah, I have just shown. Okay, you note down. I have already shown on that slide. Email and Facebook both. Can you see that slide? Presentation slide. Here is my mail ID.
Yes.
pkjain@IITTMJ, and the Facebook is pkjain2006. LinkedIn as also pkjain2006. Okay, fine.
Okay, sir. Thank you so much.
Thank you, Mike. Okay.
Thank you on behalf of Department of Mechanical Engineering IPS Academy for your kind association with us, sir. Thank you.
Okay, thank you, Mike. May I leave now the meeting?
Yes, sir.
Thank you.
Thank you all the participants for being with us in this session, and the next session will start by 2:30. That will be by SK Rajiv Nair, sir. He is a corporate relation manager, and they will be take session on beauty of inner engineering through yoga and meditation. It's a mandatory from the Atal project AICT. There will be a session, one session on this beauty of inner engineering. So I hope all you will be participate in that session, and it will be very interactive session by Rajiv Nair sir. So we will meet at 2:30. Thank you so much.